Hello everyone, this is Jesse Crawford with Tarleton State University, and this is going to be a YouTube video covering Chapter 8 of the course on hypothesis testing. As you can see, I've prepared a study guide for this chapter that is very similar to the study guide that we looked at for the confidence interval material. Now, you'll notice that this study guide roughly has two important parts. So the front page is just a very general overview of hypothesis testing and some of the key ideas that come into play with hypothesis testing, like the difference between one-tailed and two-tailed tests, the difference between a z-test and a t-test, information about rejecting H0, and there's also a bit here about type 1 and type 2 errors. I would say that this is a fairly low priority for us. I may discuss this a bit at the end of the video. This is not huge, but if you really want to understand hypothesis testing, this is sort of essential to really having a good conceptual understanding of what we're doing. Now, in addition to this first page, I also have included a single page for every different type of hypothesis testing procedure that we're going to go over. And just like with the confidence interval study guide that I gave you guys, there's information on how to conduct the test, and then there's an example in each case. What I'm planning to do here is go over the general perspective and then go through these individual examples with you. But before we can really get started, I do think we want to look at an example, because a lot of this stuff on the first page is not really going to make that much sense unless we look at an example. So let's go ahead and look at this first example on page 2. Okay, so this says, consider a population of men whose average weight mu is unknown, and assume the population standard deviation is 30 pounds. In a random sample of 2,000 men from this population, weight is 181.6 pounds. Perform the following hypothesis test at the alpha equals 0.05 significance level. And then the hypothesis test that is given is right here. So the way that we read this hypothesis test is we say that this is H0 mu equals 180 versus HA mu not equal to 180. Now, again, in the context of this problem, mu is the average weight of the men in this population. So mu is the population mean. Now, that population mean mu is either equal to 180 or it's not. So one of these statements is true and the other one is not true. We don't know which one is which right now. And so essentially, the way you can think of these two things is each one of these represents a competing hypothesis that's describing what we actually know about the population mean, what actually is true or what isn't true. These are two competing hypotheses, and they have a name. The one on the left is called the null hypothesis, so H0 is called the null hypothesis, and the one on the right is the alternative hypothesis. That's why there's a little subscript A here. So this is the alternative hypothesis. Now you might say, why are we focusing in on 180? Well, this is just the question. This is just what the problem asked us to do. It says, conduct this hypothesis test. But you can imagine a situation like a clinical situation where you actually, for whatever reason, specifically care about the value 180 for some reason or another, and you need to conduct this test. Okay, so that's kind of the first thing. It's just this idea of what is a hypothesis test? A hypothesis test has a null hypothesis and an alternative hypothesis. And our goal on this problem is to use the data that's given to us in the example. And based on that data, we are either going to reject the null hypothesis or we will not reject the null hypothesis. Now, generally, it's not really a good idea to say that you're going to accept the null hypothesis. Some books say this. It's really not correct to do that. You should either reject the null hypothesis or not reject the null hypothesis. Now, there is another important parameter in this problem. You'll notice it says we're going to use an alpha equals 0.05 significance level. And in a way, this kind of corresponds to the confidence level that we had when we were doing confidence intervals. In fact, if you think back to confidence intervals, we would always take the confidence level and subtract that from 1, and we would call that number alpha. So for example, if we had a confidence level of 95%, we would do 1 minus 0.95. That would give us an alpha of 0.05. And that really is pretty accurate here, that when you see a hypothesis test with an alpha of 0.05, there is some sense in which that sort of corresponds to a confidence level of 95%. Now, what does alpha really represent? Well, if we come back to this slide, this says that every test has a significance level alpha, and generally alpha is a small number, like alpha equal to 0.05. And when you're doing a hypothesis test, there are really two types of mistakes you can make. There are two types of errors that can occur. One thing that you can do is whenever H naught is true, you can reject H naught. Obviously, that's an error. If H naught is true, we don't want to reject H naught. So if we do that, that is an error, and it's called a type 1 error. So this is one of the types of errors we can make when we do a hypothesis test. The other type of error we can make is whenever H naught is false, we can fail to reject H naught, and that will also be an error, which is a type 2 error. Now, the probability of making a type 1 error, that's actually what alpha is. And again, because alpha is generally a small number like 0.05, that means the probability of making a type 1 error is going to be small. The probability of making a type 2 error is quite a bit more complicated. That requires something called a power analysis, and we're not going to cover that in today's video. That's beyond the scope of this video, but that might be something that we can get into later in the course. Okay, so again, the setup for hypothesis testing is basically the following. We are given a hypothesis test to perform, which is a null hypothesis versus an alternative hypothesis. We're given a bunch of data in the problem, and we're also given a significance level. And with these three ingredients, we can tie this all together to do the hypothesis test. So now that we've seen all of this, I do want to go back to this first slide and just go over the big principles. Let's talk about these, and then we'll go case by case through each of the different types of tests and talk about them. So one of the things we're going to get into today is there are two types of tests we're going to look at. There's a one-tailed test and two-tailed tests. Any hypothesis test you do is going to be one of these, one-tailed or two-tailed. And for the purposes of today's discussion, if our alternative hypothesis contains a not equal sign, that is going to be a two-tailed test. If it contains a less than or greater than sign, it's going to be a one-tailed test. And whenever we're dealing with two-tailed tests, there's a certain point in the procedure when we're going to divide alpha by 2. There's also a certain part in the procedure where we're going to calculate something called a p-value. We can get into that in a moment, but we will need to double a certain probability calculation when we're computing that p-value. So on two-tailed tests, we do divide alpha by 2, and we do double the p-value. On a one-tailed test, you don't do those things. You don't divide alpha by 2, you don't double the p-value. And again, a lot of this is going to make a lot more sense once we've seen an example, but I do just want to go through these general principles first and just sort of set the stage for what we're doing. Now, the second thing we're going to see on these hypothesis testing problems is a distinction between z-tests and t-tests. And generally, z-tests are used for large sample problems involving population means or proportions. When we're doing a z-test, we just need to keep in mind that z really stands for standard normal. So we're going to be using the inverse norm command to get the critical values, z alpha and z alpha over 2. And we will use norm CDF to find p-values. By the way, another name for p-value is observed significance level. So if you see that's just another word for p-value. And we'll have an opportunity to say what a p-value is in a moment. Now, on a t-test, those are generally going to come up for small sample tests involving population means. Notice proportions are not here. So you're never going to use a t-statistic on a population proportion. It's generally for small sample involving population means. Well, t-tests are going to involve the t-distribution. So that means you're going to use inverse t or a t-table to find your critical values, t alpha and t alpha over 2. And you'll use a t-CDF to find p-values. The last thing here is we said a moment ago that on each problem we're either going to reject H naught or we will not reject H naught. The question is, when do you do it? Each test that we look at is going to define a rejection region, and we are also going to compute a test statistic. If our test statistic is in the rejection region, we will reject H naught. If our test statistic is not in the rejection region, we will not reject H naught. Now, a moment ago, we were talking about calculating something called a p-value. It turns out you can actually make a decision about rejecting H naught using the p-value. If your p-value is less than or equal to alpha, reject H0. If your p-value is greater than alpha, don't reject H0. And these two methods are completely equivalent. So if you're worried about, well, which one should I use? Like, am I going to be getting into a bad position if I do one of these instead of the other one? That's not a concern. If you use the first set of procedures, the result you get will be exactly the same as if you use the second set of procedures. By the way, this is a really good opportunity to talk about kind of what a p-value means. You notice this says if p-value is less than or equal to alpha, we reject H0. Now, keep in mind, alpha is a small number. Alpha is like 0.05. So if p-value is less than or equal to alpha, that means it's small. And when we have a small p-value, we reject H0. In other words, small p-values are evidence against H0. And actually, the smaller the p-value is, the stronger the evidence is against H0. And that's really a good way to interpret what a p-value is telling you. Okay, guys, well, with all of these general principles under consideration, and now that we've went over these, why don't we actually go through and look at the procedures that we're going to do. So basically, hypothesis testing is pretty straightforward once you kind of have the general idea under control. Every hypothesis test we're going to look at, it's basically a three-step process. You're going to calculate a test statistic. Once you calculate that test statistic, you're going to compare it to a critical value using a picture like this. And then finally, you're going to compute a p-value. Now, step 2 and step 3 are really the same for every test problem, every testing problem we're going to look at. The only thing that really changes is the test statistic itself. And how does this get computed? Well, you'll notice that every one of these settings in the study guide, I basically am giving, this is the situation when you use the test and when you actually apply it. And then I tell you what the test statistic is here, and sometimes have some additional comments that may be important. So let's actually take a look at this. So the first type of test we're looking at is the large sample hypothesis test for a population mean. We're going to use this when we have a random sample from our population and our sample size is large. And again, for the purposes of confidence intervals and hypothesis testing, a large sample means that n is greater than or equal to 30. That doesn't really mean that it's large enough to obtain really high quality statistical results. Generally for that, you want at least a sample size of about 500, maybe 1,000 or 2,000. That's generally the sample size you're looking for. But in terms of the difference between a z statistic and a t statistic, the cutoff is 30. And that's really what we're talking about in this study guide. So when we have a large sample size, our test statistic is going to be z equals x bar minus mu naught divided by sigma over the square root of n. Now this is if we know what sigma is, if we know what the population standard deviation is. If we don't know what the population standard deviation is, we're going to use the sample standard deviation s, but this is basically the same formula, and in both cases we do get a z statistic. Now some books will actually put a t statistic here, but the thing is, whenever your sample size is large, the t statistic is approximately equal to a z statistic anyway, so don't sweat that. Just feel free to use the z statistic in this case. So let's get back to our example. So the example that we're looking at is consider a population of men whose average weight mu is unknown. Assume the population standard deviation is 30, and we're looking at a random sample of 2,000 men, and the average weight is 181.6 pounds. We're trying to perform the following hypothesis test, mu equals 180 versus mu not equal to 180, and we're looking at an alpha equals 0.05 significance level. Let's go through this step by step and just show how this procedure works. So again, every problem, step 1 is computing a test statistic. Now, obviously on this slide, we're going to use the formula up here to do that. But let's imagine you're on a homework problem or a test problem, and you're not exactly sure which procedure to use. What do you need to do? Well, in this problem, we're looking at quantitative data, and we're looking at a population mean mu. Okay? So there's population means and population proportions. Population means are mu, and population proportions are a variable p, right? Now, basically, this population proportion kind of stuff, this is when you're looking at binary problems, like you're looking at whether someone approves of the mayor or not. Apologize for that. You're looking at whether someone approves of the mayor or not. That's either a yes or a no. That's a population proportion. But a population mean is something like quantitative data, like you're talking about the weight of a person or the height of a person or someone's cholesterol level or blood sugar level or something like that. So when you're dealing with quantitative data, that's a population mean. And when you have a large sample, that tells you you're going to use this test statistic here. Now, this is really a piece of cake, right? We just take our test statistic, take all the information from the problem. So this gave us a population mean of 181.6, so that's our X bar. Now, mu naught, what is that? Well, that's just the number that's in your null hypothesis, right? So you're just going to take this 180, plug that in here. Our population standard deviation is 30 pounds, so that's going to come here, and then our sample size is 2,000. That's going to plug into the formula here. So you just plug all these variables into your test statistic formula, do the calculation, we get 2.39. And that's step one. So step one is just calculating a test statistic. Now we go to step two. So step two is to draw a picture like this of a normal distribution. And we need to identify critical values. So that's where this blue region is. And basically the blue region is the rejection region. And the white region in the center is where you don't reject. So if you land in the rejection region, you do reject H naught. If you land in the middle, you don't reject H naught. Okay, now we saw in the previous slide, if our alternative hypothesis has a not equal sign, it's a two-tail problem. So you can see right here, alternative hypothesis has a not equal sign. This is a two-tail problem. On a two-tail problem, you will always take alpha and divide it by 2. So we're going to take our 0.05, divide that by 2, we get 0.025. And then because this is a z statistic, z stands for normal. Therefore, we are going to use an inverse norm calculation to get our critical value. Now, Z really stands for standard normal. So you're going to do inverse norm here. This is the 0.025 tail probability, but standard normal means that the mean of that standard normal is 0, the standard deviation of that standard normal is 1. So you're going to type all that stuff in. And when you do this on your calculator, you're going to get negative 1.96. Now, what you really need to do is just kind of disregard that negative sign. You can see that I've put little absolute value bars around this calculation, which basically just means ignore the negative sign, you get positive 1.96. And 1.96 is right here. It's the critical value that separates that center region from the critical rejection region. Now, of course, because this is a two-tail problem, you also have the corresponding value on the left-hand side of negative 1.96. So if you land in either one of these tails, you're going to reject the null hypothesis. Now, our test statistic was 2.39. You notice that we've landed right here, and we are in the rejected region. And therefore, the conclusion here is that we do reject the null hypothesis. So let's actually just pause for a second and think about clinically what this means in this problem. So our hypothesis testing problem was null hypothesis says that the average weight of the men in this population is 180 pounds. The alternative hypothesis is that mu does not equal 180. What we've been able to do here, we've been able to reject the null hypothesis. And what that means is we have strong evidence that the null hypothesis is false. And if the null hypothesis is false, then that means we have strong evidence that the alternative hypothesis is true. And that's how you want to think about that. So yeah, let's go ahead and continue on though and do the last step of this problem, which is to compute the p-value. So the last thing we want to do is compute this p-value. How does that work? Well, you'll notice that, again, our test statistic was 2.39. That's right here. That's that little red mark in this picture. What the p-value does is it says, go ahead and shade that red mark to infinity and also do the mirror image on the left-hand side and calculate that probability. That's what the p-value is. Well, how do we do that? Well, this is a standard normal curve, right? So to calculate this probability, we're going to use our norm CDF function on our calculator. We're going to go from 2.39 to infinity. And again, on our standard TI-84 calculator, our proxy for infinity is sort of like 10 to the power of 99. That's the biggest number we can do. But again, this is a standard normal curve. So it has a mean of 0 and a standard deviation of 1. Now, this norm CDF calculation is that little red probability right there. But we also care about the red probability on the left-hand side, right? We actually want both, and that's why we need to double this calculation. And you can see at the beginning of this, I actually have 2 times norm CDF of all of this stuff. And when you do that entire calculation, in this case, you'll get 0.0168. Now, as stated earlier, the smaller a p-value is, the stronger the evidence is against H naught. And in particular, if your p-value is less than alpha, you will reject H naught. Now in this problem, our alpha is 0.05. Our p-value here is 0.0168, which is quite a bit less than 0.05. And so we're going to reject H naught. Now you'll notice that in step 2, we already rejected H naught. And this is what I was saying earlier. The p-value will always lead you to the same conclusion that the critical value leads you to. These are two different methodologies for doing a hypothesis test. And it's really important that we understand both methodologies because you may see journal articles that use this sort of critical value approach to hypothesis testing and test statistics and that kind of thing. You may also see journal articles that are using p-values. So you do want to be familiar with both methods and be prepared to sort of interpret both of those. Okay, but that's it. That's it for this first example, guys. Pretty straightforward. We just take the data in the problem, use that data to compute a test statistic. We use a method that we've discussed to find critical values, draw a picture. If your test statistic is in the critical region, you reject H naught, and then you simply shade that value to infinity, and in this case also to negative infinity because it's a two-tailed test, and that allows you to calculate your p-value. So actually, now that we've done this first example, a lot of the methods should be clear, and now we just need to talk about what we do in each of these additional settings. So this next setting is now we're going to do a small sample hypothesis test for a population mean. What is the big difference here? The big difference is that this is generally going to result in a t statistic in this case. Now, to be more precise, the t statistic occurs when your samples, when your population standard deviation is unknown and you have to deal with the sample standard deviation s. If you actually know the population sigma and you can put that in here, it actually is still a z statistic, but this is usually not going to happen. I'll just tell you that. Most of the time in a real problem, this is where you're going to be and you are going to have a t statistic. Now, as a reminder, we know on any t statistic we have degrees of freedom. And then this simple situation, it's just going to be n-1 right here. All right, let's look at a problem. So this says, according to an environmental regulation, mean emissions from vehicles must be less than 20 parts per million of carbon. In a random sample of 25 cars of a certain type, the average emissions level was 19.47 parts per million, with a standard deviation of 1.78 parts per million. Assuming the population is normally distributed, test whether the average emissions level of this type of car is less than 20 parts per million using a significance level of alpha equals 0.05. Now you might be wondering, why did it mention this thing about assuming the population is normally distributed? And the reason this is important is because on a small sample hypothesis test, it's actually only possible to perform it whenever your population is normal. So this assumption is necessary on this type of problem. If we go back to the large sample problems, that doesn't require the population to be normal, because when you have a large sample size, there's a mathematical theorem called the central limit theorem that steps in and makes it to where you don't need to worry about that in that situation. Okay, let's do our three-step process here. So step 1, we are going to calculate our test statistic. You'll notice this t statistic, it's really just the same formula we used on the previous slide. So you just take your sample mean, 19.47, keeps popping up, but we'll take our sample mean of 19.47 here. We're going to take mu naught is the 20 from our null hypothesis. Our standard deviation is 1.78, and our sample size on this problem was 25. Plug all that in, we get a test statistic of negative 1.49. Then step 2, we go to critical values. Now on this problem, our alternative hypothesis has a less than sign. So if you see a not equal sign, it's a two-tail problem. If you see a less than or a greater than sign, it's a one-tail problem. So this is a one-tail test. And because it's a one-tail test, we do not divide alpha by 2. We just leave alpha alone. So alpha on this problem is 0.05. Now, because this is a t-test problem, we are going to use either an inverse t command or a t-table to get our cutoff value. And again, we care about our degrees of freedom. Our degrees of freedom here is n-1, which in this problem is 24. So you would just do an inverse t calculation. Again, don't divide your alpha by 2, right? It's just 0.05, 24 degrees of freedom, get rid of the negative sign, and you're going to get 1.711. And this is going to happen if you do inverse t or a t-table. This is what you're going to see. So now let's draw a picture of this. Now, notice that this picture only has one tail, right? This is a one-tail problem. It's not a two-tail problem. So the question is, which tail are you looking at? The tail that has the rejection region is going to be the one that corresponds to the alternative hypothesis. If this alternative hypothesis says that mu is less than 20, that is going to be on the left tail. If this says mu is greater than 20, it's going to be over here on the right tail. So since this is a less than sign, we're actually going to look at the left tail here. Now, the cutoff is 1.711, but of course that actually is negative here because we're on the left side. So this cutoff is negative 1.711, and our test statistic is negative 1.49. So we're not actually in this tail, right? We're not actually in this critical region. In fact, if you look at this picture, this little red marker is sort of in this white region, right? It's not actually in the blue rejection region. So in this problem, we do not reject H0. That's actually what our result is. And again, we can talk about our p-value in a second, but I do actually want to interpret the clinical meaning of what this would say on this problem. So let's think about what's going on here. We're looking at an environmental regulation. And imagine, put yourself in the position of someone that's manufacturing these cars. You want your cars to be able to go to market. But according to this environmental regulation, the average emissions from the vehicles must be less than 20 parts per million. So you actually want to reject this null hypothesis because you want to demonstrate the alternative hypothesis is true. You actually want those cars to have emissions less than 20. But in this problem, we do not reject the null hypothesis, which means we have not been able to demonstrate that the null hypothesis is likely to be false, which means we have not been able to demonstrate that the alternative hypothesis is likely to be true. And so what would happen in this situation is these cars would likely just not be approved to go to market. The environmental regulation would not allow that. A big part of why this is occurring is just because the sample size is so small, right? We've got a sample of 25 cars, and in this sample of 25 cars, we even have an emissions that's less than 20, but it is not statistically significantly less than 20. This 19.47 is really not that much less than 20, and there's still a chance that the mean emissions are really greater than 20 in the population. So yeah, this is a situation where we would not be able to reject the null hypothesis. Now, earlier I said we do not generally accept the null hypothesis. And that is sort of for some technical reasons that maybe we can discuss in a later video. But basically, here's a very simple guideline that explains why this is true. Whenever you reject the null hypothesis, like on this problem up here, when you reject the null hypothesis, you actually do have strong evidence that the null hypothesis is false. Whenever you fail to reject the null hypothesis, like in this problem here, we did not reject the null hypothesis. You do not have strong evidence that the null hypothesis is false, clearly, right, because you're not rejecting it. But on the other hand, you actually don't have strong evidence the null hypothesis is true either for mathematical reasons that we don't need to go into right now. So what happens when you don't reject H0 is you really don't have a strong decision either way. You don't have a strong decision against H0, but you also don't have a strong decision in favor of H0. And that's why you really don't want to say things like accept the null hypothesis. You don't want to say that. You will sometimes see books that do that, though, so just fair warning, but that's really not a good practice to get into. Okay, but let's go ahead and move on to step 3 and compute our p-value. So again, what do you do with your p-value? You take the test statistic you got. The test statistic we got was, the test statistic we got was negative 1.49. And we want to take that negative 1.49 and shade it. Now, again, in this problem, it's a one-tail problem. We're not going to shade both sides. We're just going to shade towards our rejection tail. This is what we get. We need to calculate this probability. How do we do that? Well, this is a t-distribution. So we are going to do a t-CDF, and we're going to go from negative infinity right here to negative 1.49, right? So you can see that here. Negative infinity to negative 1.49. And we do have 24 degrees of freedom. And you'll notice we get about 0.0746, which is also the one that's given in this picture. Earlier, we talked about how when the test statistic is less than alpha, you reject H0. When it's greater than alpha, you do not reject H0. Notice in this problem, alpha is 0.05 And this test statistic is greater than 0.05. And so again, we do not reject H0 in this problem. All right, guys, let's just keep on trucking here, go through the rest of these cases. Now we're looking at hypothesis tests for population proportions. Again, population proportions come up when you're looking at binary data, yes or no. So in this problem, we have a random sample of 200 people from a certain town, 115 people approved of the mayor's job performance. We want to test whether the proportion of people in the population approving of the mayor exceeds 0.5 at the alpha equals 0.05 significance level. And again, a different way to write this would be H0 P equals 0.5 versus HAP is greater than 0.5. Now, one thing you'll notice right away is these previous problems, they had a mu here, right? Because that was a population mean. On this problem, we have a P because this is a population proportion for binary data. Again, we want to test whether the mayor's approval rating exceeds 0.5. So you can see our null hypothesis says it's equal to 0.5. Our alternative hypothesis says it's greater than 0.5. I do want to point out, by the way, this number 0.5 is different from this number, alpha, which is 0.05. Right? So these are different numbers, and just be careful because sometimes it's easy to mix those up, but these are two separate numbers in this problem. All right, let's run through this here. You guys all know that on population proportions, we need to get a p-hat. So we're just going to take the 115 over 200. That's going to give us 0.575. And then this is our test statistic. So we're just going to have 0.575. That's the number we just got. And then this is minus p-naught. So that's 0.5. And then we also have down here p-naught and q-naught. As a quick reminder, p-naught here is 0.5. Q-naught is just 1 minus p-naught, right? So if p-naught is 0.5, q-naught will be 1 minus 0.5, which also happens to be 0.5 in this problem, but in other problems, those would be two different numbers. And then we have our sample size n, which is 200. All of the stuff in the denominator is under this radical. So just be kind of careful about how you type this into your calculator. When you do this calculation, you'll get 2.12. Okay, let's look at our critical value. And at this point, this should start to become pretty much smooth sailing. We've already done this a few times. It's pretty clear what we're going to do. Our alternative hypothesis has a greater than sign. That means this is a one-tailed test. Our alpha is 0.05. We do not divide that by 2. This is a z statistic, so we do inverse norm. We, again, don't divide by 2. We end up getting 1.64 as our critical value. You can see that in the picture here. Our test statistic is 2.12, so that does land us in this critical region, and so we do reject the null hypothesis. The clinical meaning of this in this problem is the null hypothesis here says that p is equal to 0.5. The alternative hypothesis says p is greater than 0.5. Now, you might wonder, what about p less than 0.5? That is actually contained in this null hypothesis, even though it's not written this way. You might argue this really should say p is less than or equal to 0.5 versus HAP is greater than 0.5, and that's actually valid. For whatever reason, for sort of traditional, conventional reasons, we just don't write it that way when we do hypothesis testing. The null hypothesis will always say equals. The alternative hypothesis could say pretty much several different options here. But we have rejected the null hypothesis here, right? So we are rejecting this. So we have strong evidence against this. That means we have strong evidence in favor of this. So we actually have statistically significant evidence in this problem that the mayor's approval rating in this town exceeds 0.5. Another way to think of that is the approval rating is higher than 50%. And that's really good, right? Because when this mayor goes up for re-election, it'll be nice to have more than 50% approval rating in the next election there. And then, as you would expect, the p-value calculation is pretty similar to what we've done before. You're just going to take your test statistic of 2.12, shade that. Again, this is a one-tail problem. We're only going to shade one side. So we'll just shade to infinity here. And this is a z statistic, so we are using the normal distribution to calculate this. So we're just going to do a norm CDF from 2.12 to infinity. Go ahead and put a 0 and 1 here. We get 0.017. And again, that's less than alpha, so that confirms our decision to reject H0 in this problem. Okay, so that's the last scenario that we were going to talk about in this study guide. But there is actually one more topic I wanted to touch on a little bit. I don't think a discussion of hypothesis testing can be complete without some discussion of type 1 and type 2 errors. So let's get into this a little bit. And what this discussion will really do is help us to understand why we are allowed to reject the null hypothesis, but we're never really allowed to accept the null hypothesis. So let's just look at this a second time. So there's basically two possibilities. H naught is either true or it's false. And then there's two things we can do. We can either reject H naught or don't reject H naught. If H naught is true and we reject it, that's an error. It's a type 1 error. If H naught is false and we don't reject it, that's a type 2 error. In the other two cases, we're actually making the correct decision. Now, what we've seen in this guide is that every test has a significance level alpha, and it's generally a small number like 0.05. But you might have been wondering, what is alpha? What does it actually represent? And this tells us the probability of making a type 1 error is at most alpha. Now, you might wonder, why does this say at most alpha? Why doesn't it just say the probability of making a type 1 error is alpha? And the answer is the following. If H naught is false, you can't make a type 1 error, right? The only way you can make a type 1 error is if H naught is true and you reject H naught. That's how a type 1 error occurs. So if H naught is false, you can't make a type 1 error. That means the probability of a type 1 error in that situation is 0. However, if H naught is true, you can make a type 1 error. And in that situation, the probability of a type 1 error is alpha. So what's really going on here is the probability of a type 1 error is either alpha, which is a small number, or it's 0, which is really a small number, right? And what that really tells us is the probability of making a type 1 error is small. That's really important. What about a type 2 error? Well, it turns out calculating the probability of a type 2 error requires a more complicated procedure that we will not cover in this video called a power analysis. And to make a long story short, the probability of a type 2 error can be quite large. And there is actually nothing we can do to make the probability of a type 1 error and a type 2 error simultaneously both small. The only thing you can make the only way you can make the probability of both of these errors go down is to make your sample size larger, but that requires more resources, and in every statistical problem you have limited resources. So you can't just have an infinite sample size. So let's just kind of summarize this by saying the probability of a type 1 error is small because it's at most alpha, and alpha is a small number. The probability of a type 2 error could be big. And now, with those points in mind, let's actually think about what we've done on these hypothesis tests to see why we are allowed to reject H naught, but we're not allowed to accept H naught. So let's actually look at this example again real quick. So in this problem, we got a test statistic of 2.39. That was in our critical region, and so we are rejecting H naught. And what I said in this situation is that, yeah, we can be quite confident that H naught is really false, and we really can reject it in favor of the alternative hypothesis. But why is that really possible? Why are we allowed to do that? Well, let's think about this. We're rejecting H naught, right? Well, let's go back, given that we're rejecting H naught, and let's think about what kind of mistake we could be making. We are rejecting H naught. What kind of mistake can we be making? Well, we could be making a type 1 error or the correct decision. We cannot be making a type 2 error right now. But the probability of making a type 1 error is small. It's at most alpha. And what that means is generally when you reject H naught, the probability that you're making a mistake is pretty low. The only mistake you could be making is a type 1 error, and the probability of a type 1 error is small. And so you can be quite confident when you reject H naught that you really are making the right decision. And the smaller alpha is, the more confident you can be. And for that matter, the smaller your p-value is, that's even more confident, right? So what this really is telling us is when you have a p-value of 0.0168, let's just round that to 2%. So this is a p-value of roughly 2%. You can almost interpret that as like a confidence level of 98%. You can sort of view it that way, that that's how confident you can be in your decision to reject H naught. Okay, so that's what's happening when you reject H naught. What about when you don't reject H naught? So let's go down in this example. So this is an example where we got a t-statistic of negative 1.49, and that means we were not in our critical region, and that means that we did not reject H naught. So If we are not rejecting H naught, does that mean that we can accept H naught? Well, let's actually go back and look at our table again. So if we don't reject H naught, the type of error that we could be making is a type 2 error, but we have absolutely no control over the probability of a type 2 error without doing a power analysis. And I'll just say, even when you go into a power analysis, it's not really a completely satisfying result. When you're making a type 2, when you're not rejecting H naught, you can always be making a type 2 error, and there's really no safeguard against the probability of a type 2 error being large. And so for that reason, you don't want to say that you accept H naught, because if you accept H naught, you could be making a type 2 error. You don't have control over that. So the way that you can protect yourself is to simply say, look, I'm not rejecting H naught, but I'm also not accepting H naught. And that way you've kind of covered your bases. So if we go back to this example down here, we're basically trying to figure out, is mu equal to 20 versus is mu less than 20? We're not going to reject H naught. We're also not going to accept H naught. And this was the example that we did about environmental regulations for vehicles. And I really think the most likely outcome in this problem would be that this company would just need to do more study. They would need to go back to the drawing board. They only took a sample of 25 cars. They really need to go back, take a larger sample, get more data, and then hopefully for them, they will get a test statistic that's better, which will actually now allow them to reject the null hypothesis, which will provide strong evidence that their emissions levels meet the standard, and they will be able to take their cars into the marketplace. Okay, guys. Well, as always, I appreciate you watching this, and I hope this was helpful. If you have any additional questions on hypothesis testing, just feel free to shoot me an email or post a question in the homework and lecture help form on Canvas. Without further ado, I'll see you next time.